number 7. I use a rope 2 meters long to swing a 10-kilogram weight around my head. The tension in the rope is 20 newtons. In half a revolution, how much work is done by the rope on the weight? There are two ways I'm going to talk about this coming out to be 0. One is that work is force times distance times the cosine of the angle between them. Here theta is 90, so we would have 20 newtons times our distance of half the circumference, pi, times 2 times the cosine of 90 degrees. So the cosine of 90 degrees is 0, so that comes out to be 0. Another way of thinking of the work is the change in kinetic energy. So the change in kinetic energy at the beginning is 1/2 mv squared, and the kinetic energy at the end is also 1/2 mv squared. So assuming that the velocity does not change, that will come out to be 0. So the answer is D. Number 8. Which of the following is that form of energy associated with an object's location in a conservative force field? And recall that gravitational potential energy is mgh. H is a position. Spring potential energy is 1/2 k x squared. X is a position. Gravitational potential energy in the case of the universal gravitational potential is negative mg mass times gravity over rm, big M, little m, and r is a location. So the answer is potential. All of those have potential in common. Thermal is associated with temperature. Biochemical, I guess, I don't know, associated with calories. Kinetic is a function of the object's velocity. And I'll just go with this one, mc delta t, or PV equals nRT temperatures, just for future reference. Number 9. A golf ball hits a wall and bounces back at 3/4 of the original speed. What part of the original kinetic energy did the ball lose in the collision? So, our starting kinetic energy, let's put this as a ratio. What part of the original kinetic energy of the ball did it lose in the collision? So our ratio is going to be kinetic energy initial divided by kinetic energy final, which is going to be 1/2 mv squared divided by, and then at the end it's 1/2 m. We've got 3/4 of the velocity squared. So everything cancels except 1/3/4 squared, which will be Okay, I've set up my ratio backwards, but we will actually want final over initial. But this comes out to be 16 over 9, or 16 over 9, and the final over initial is 9/16. So the answer is D here. Number 10. A rock is thrown straight up with an initial velocity of 15 meters per second. Ignore energy loss to air friction. How high will the rock rise? So we've got an initial velocity, 1/2 mv squared. How high will that's our initial kinetic energy should be equal to our final potential energy. So divide by gm, and we'll have h equals 1/2 v initial squared over g. So cancel out the m's. We have 2 over g. Yeah, h final. So 1/2 15 squared over 9.8 is equal to, it's funny because I forgot to divide by 2 at first. I got 22.959. I was like, okay, that rounds up to 23. And then they had 22.9 there. But that didn't round right. So that would have been nice of them. But anyway, the answer is 11.5 meters. So, number 11. A simple pendulum, 2 meters in length, is released by a push when the support string is at an angle of 25 degrees from the vertical. If the initial speed of the suspended mass is 1.2 meters per second when at the release point, to what maximum angle will it move in the second half of its swing? Okay, we have a simple pendulum, 2 meters in length. Let's call that R. R equals 2 meters. Is released by a push when the support string is at an angle of 25 degrees from the vertical. If the initial speed of the suspended mass is 1.2 meters per second when at rest at the release point, to what maximum angle will it move in the second half of its swing? The hint down here says h equals r times 1 minus cosine theta. What does that mean? Well, we've got an angle of 25 degrees here. That's how far the ball is above the release point, or above the bottom. So this distance h is equal to the full length of the pendulum, 2 meters, r, minus r cosine theta, which is going to be the 2 meters here times the cosine of this angle here. So what we can do to solve this is that the total energy at the beginning, 1/2 mv squared plus mgh initial, or mg r times 1 minus cosine theta initial. All of this whole thing is just going to be a number. All of those values are known. Well, actually, no, we don't know the mass. But at the end, everything is going to be in the form of potential energy, and it'll be the angle that it rises to on the other side because they gave it a push. So this will just be mg r times 1 minus cosine theta final. Ran out of room there. Okay, so just plugging in the numbers, 1/2, we can cancel out all of the m's because there's an m in every term. 1/2 v squared times 2 squared plus 9.8 is g times 2 meters times 1 minus cosine of 25 equals gr, I'm going to put that on the bottom over here, 9.8 times our r value is 2 meters equals 1 minus cosine theta final. So all of this comes out to be 0. And you can tell from the multiple choice questions, they were expecting me to make that error, because technically this was 36.4, 46047808, and that does not round to 37 degrees, that rounds to 36 degrees. And so they got me. What happened was, when I was doing 1/2 v squared, I put in 2 instead of 1.2. And when I do that, let's erase this, and erase this. So this comes out to be 0.5. Okay, now I got it. 1 minus cosine theta is 0.1304, cosine theta is 0.8695, and theta is 29.59, which rounds up to 30.